All right. I think we will get started now, and whoever filters in can, join us in progress, I guess, in media res. Thank you for coming today to our Spatial Analytics and Data seminar, where today we are hosting Kevin Mwenda, who's talking about quantifying spatial uncertainty of reported COVID cases using the restricted and controlled Monte Carlo process. Um, uh, Dr. Mwenda joined the faculty at Brown University in 2018 as an assistant professor of population studies at the Population Studies and Training Center. He's also the associate director of the Spatial Structures in the Social Sciences, or S4 initiative at Brown. Dr. Mwenda's research focuses on spatial disparities in health outcomes among vulnerable populations around the world and how these patterns are influenced by various environmental, climatic, and socioeconomic factors. So I'm sure today's talk will be plenty interesting and plenty topical. With that in mind, please also remember to submit questions using the Q&A functionality in Zoom. At the end of the talk, we'll have about 10 minutes for Q&A, so please do make sure to do this because it'll really help to have a robust discussion at the end. Finally, make sure to submit those at any time, so definitely just post them as we go. So with that said, I'll now turn it over to Kevin to let him present.
Thank you so much, Levi. Thank you, Rachel. Thank you to all the partners for this talk today. It's my pleasure to be here and to offer some insights on some work in progress. And this work entails some fine-scale mapping of COVID cases in the context of the state of Rhode Island in the US. And thank you to all the participants for sparing the time to be here. So I'm just going to go ahead and share my screen and we'll get started. So hopefully everyone can see that. Thank you. Thank you, Levi. Thank you, Rachel. So yes, as Levi introduced the topic today, the talk is entitled Quantifying Spatial Uncertainty of Reported COVID Cases using the Restricted and Controlled Monte Carlo, or the RCMC process. So I'll say a little bit about what that is, but first, let me talk about the highlights of this talk, all right, just to give a little teaser of what to expect by the end of the next few minutes. So we'll be talking about some methods behind disaggregating polygon-level location data using the RCMC process. And in so doing, we'll be estimating local disease intensity, and the disease here is COVID, by example, using the kernel ratio estimation method, the KRE method. And then we'll be estimating the statistical significance of the local intensity using another process known as the unrestricted but controlled Monte Carlo process. All right, so these are some processes that allow us to basically disaggregate data from a polygon level to a fine scale level that could be depicted by points, for example. Just as background information, the kernel ratio estimation method is an extension of the kernel density estimation method that some of you might know about, which is a widely used spatial analytical method for estimating local intensity. So where the conventional KDE, or the kernel density estimation method, assumes a homogeneous background, the kernel ratio estimation assumes that there's some variation in the event points, in this case, disease cases, and the background, which is the population at risk. So the ratio between those two is what we call the kernel ratio estimation method. So the motivation for this talk and the work that is in progress is basically to try and understand COVID from a fine scale perspective, right? So the pandemic has affected people from all walks of life, both the illness itself and the subsequent effects that have been felt differentially across residential communities and demographic groups. So we wanted to take this set of methods that have been used for modeling uncommunicable diseases, such as lung cancer and birth defects, to see if we can take some insights from those methods and adapt those to communicable diseases such as COVID-19. So to do that, we'd have to understand the spatial distribution of COVID-19 in a certain setting, so then that way we can be justified in using such a method that has been used in a different context. So for example, for communicable diseases, we need to basically make sure that the disease incidence itself relates a certain way to the number of people in an area and the population density in that specific area. So a little background about COVID-19 in Rhode Island. So around December 9th last year, we were facing the second wave, right? So we had an incrementally high number of COVID cases and COVID deaths. So you can see those two peaks here in these, the two lines highlighted in orange. So this is data downloaded from the Department of Health in Rhode Island. And that shows you that indeed things were really dire. And so it would be helpful to understand from a fine scale perspective what the situation looked like in municipalities in Rhode Island on those dates. Okay, and this is what we see here. The map on the right shows you the cumulative confirmed cases in Rhode Island municipalities, and those are cities and towns. We have 39 of those on December 9th, right? So you see here, if you can see my cursor, that around the Providence area, Providence is the capital of the state of Rhode Island, we see that these municipalities around here had the highest quintile of cumulative cases of COVID-19. And the southern parts of the state had some of the lowest cumulative cases. So a typical map like this is what the public would see through portals such as the Department of Health. And this is useful information, shows you the cumulative cases on a municipality level. Now, using principles in geography, then we understand that what we are seeing here is aerially interpolated across the entire polygons, right? So we are unable to see insights on a scale that is finer than the municipality. So the motivation then was to explore methods that allow us to see some nuanced insights of COVID-19 cases within each of these polygons. And so to do that, I looked into some simulation methods to try and make that leap, right, for exploration of spatial heterogeneity of COVID cases. And this is where the RCMC method comes in. And before I explain what that set of method entails, the idea here is to basically look at disaggregating a specific number of disease cases. So in this case, you have one polygon, and this hypothetical example gives us a glimpse that we have 150 disease cases. But if we are able to show that the number of cases is related to the population distribution, and the population data is derived from a fine scale raster map, right? For example, at 100-meter resolution, then we can simulate the expectation that each incidence of disease is more likely to be found where you have a high number of people in that area. And so if you run the simulation several times and restrict those disease cases to the certain polygon, which we know basically encapsulates the occurrence of this disease, then we can create clusters of these diseases based on the relationships of the cases to the population. So we could look at a set of simulations and then basically derive some insights into where we'd expect to have a high incidence of disease compared to other areas. So what this allows us to do is to take these 150 disease cases in these hypothetical examples and allocate them across these polygon in a more nuanced manner rather than assuming that these 150 cases are spread out evenly. So that is what the RCMC does through a series of steps that we'll talk about in the next few minutes. All right, so let's talk about what RCMC is. So this method assigns polygon level addresses to random point locations, but this randomization is restricted and controlled. First, it is restricted by the zones, right? These polygons, in this case for Rhode Island, we're talking about the municipalities, that's the cities and the towns. So this restriction basically sets a boundary such that the allocated points or the simulated points will not be assigned outside its own zone. Second, the randomization will be controlled by the background, in this case, the high resolution population data, so that the probability of allocation to receive a subject from the randomization is proportional to the background value at that location. So the points generated by this restricted and controlled randomization will be used as actual locations of those polygon level addresses in following analysis. So the RCMC adopts a conservative strategy. It assumes that within a spatial unit, the distribution of the subjects being disaggregated follows the population. This strategy cannot reveal the actual deviation of the subjects from the population in a single spatial unit, just like any other method. It does, however, generate more realistic scenarios than the most commonly used centroid representation and the even distribution representation, like what a polygon does, and will greatly improve the analysis quality for the entire study area that contains many spatial units. So once this disaggregation happens, the kernel ratio estimation is conducted to have a series of maps depicting the intensity of cases. So that is the RCMC part of the simulation. In tandem to the RCMC, we have the unrestricted but controlled Monte Carlo, which is the UCMC. So the UCMC takes the COVID cases in the entire state and accounts for their relationship with the gridded population data for the entire state as well. So where each of the actual intensity values created by the RCMC is compared to the random intensity values generated by the UCMC, this comparison basically yields a p-value, right? So therefore, with many RCMC iterations, there will be many p-values at a location. And then their mean p-value can be considered as their representative p-value, and the variance is a measure of the spatial uncertainty sourced from the polygon level location data. So this map of the mean p-value and a map of the standard deviation of the p-value are generated as the final output for disease mapping. So the RCMC and the UCMC is repeated many times, and basically a mean p-value is generated out of this repetition of simulations. Just to emphasize again, the restriction here in the RCMC part of this process is dictated by the boundaries of the municipalities, because we know that the cases belong to a certain municipality, but within that municipality, you might not know exactly where these addresses are due to confidentiality of patient information, for example. So this RCMC process can be achieved using the Arc Health software, which is an extension for Esri's ArcGIS desktop that was created by Professor Shunshi, who teaches at Dartmouth College. Here's the link to this extension, and I can put this in the chat after this presentation. This extension works for Esri's ArcGIS desktop, version 10.5 and 10.7. So ideally, with this density mapping dialog box, you're able to put in your polygon file that has the number of cases. And then you choose the variable here. That's your zonal cases. The exaggeration factor here allows you to dictate basically to exaggerate the number of the population per pixel in case you have very low values. It assists the algorithm to run more efficiently. And then in item number 2 here, you get to select the bandwidth type. It could be either fixed or adaptive based on the expected count or the number of cases. I will talk about this later in a few slides, but I just wanted to say that for demonstration purposes, I choose the adaptive based on the expected count of 1. What that does is it tells the program to automatically calculate the population divided by the cases, right? This is the ratio that in our case comes up to 18, and this is the population threshold of the adaptive bandwidth. So the number 18 is derived by dividing the 2018 population of Rhode Island, which is a little bit more than 1 million people, by the cumulative COVID cases in December 9th, which is a little bit under 60,000. And then the adjustment side is the case side. I'll talk about this later. And then you get to choose the number of permutations for the RCMC. We've set that to 100, and the UCMC simulations, which is 1,999. Then you're able to choose the output cell size because this will be basically saved as a raster. I chose an output cell size of 500 meters resolution. And then here, I chose a place to save the output file. And I basically say that I'm only interested in the overall mean and the standard deviation of the probabilities from the RCMC process. So other parameters here is the maximum distance for the neighborhood kernel is 20,000 meters or 20 kilometers for reference. This is a subjective number that was using just for demonstration purposes. In research, this number could be informed empirically or through a sensitivity analysis. So as a fun fact, using a machine with an i7 processor, 1.8 gigahertz and a 16 gigabytes of RAM, this process took around 5 hours. So, so here are some maps of the input files in the RCMC process. So the map on the left here again is the cumulative cases of COVID by municipality. We have 39 municipalities again, as I said, in Rhode Island, and here are the cases by quintile. And then this is a population map at the 100-meter resolution derived from the World Pop website. This reflects an estimated population count in 2020. So out of the RCMC process, we have a map of the mean p-value, right? So the low p-values here show areas where you have a high certainty of high cases, of the occurrence of high COVID cases. And you have a standard deviation map of the output as well. So the mean p-value and the standard deviation maps here are at a 500-meter resolution, as depicted in the dialog box in the previous slide. So just zooming into one of these areas here, Central Falls Municipality, which is north of Providence. The map on the left shows us the population map, and the map in the middle here shows us the mean p-value and the standard deviation. Just zooming in to see that where you have the high population, you also have a significant occurrence of simulated cases of COVID, and you have a low standard deviation. So I'll talk a little bit about Central Falls, municipality in the next couple of slides. So using this information from the RCMC process, we can try to derive some measures of spatial certainty or uncertainty conversely. So figure A represents the mean of the 100 derived p-values at each location, and figure B shows the standard deviation of these 100 p-values. Figure C is a binary raster that was created by assigning 1 to the pixels with values less than or equal to 0.05 in figure A, and 0 to all the other pixels, right? So here an alpha value of 0.05 was selected as a threshold. So if no uncertainty analysis is performed, the areas with a value of 1, highlighted in red in figure C here, can be considered as areas that may have clusters and deserve further investigation. In other words, these cluster areas have a high degree of certainty. Assuming a normal distribution of the 100 p-values, the 95% confidence limit of the p-value can be calculated by adding 2 standard deviations to the mean of the p-values. Based on this idea, figure C was produced in 2 steps. First, multiplying the figure B by 2 and adding the result to the mean p-value map depicted in figure A. And second, assigning 1 to a pixel if after the addition, its value is still less or equal to 0.05 and 0 otherwise. In figure C then, the pixels with a value of 1, again depicted in red, indicate the locations for which we are at least 95% confident that the probability that the current clustering pattern occurs by chance is less than or equal to 0.05. So zooming into those areas, you see that, again, this is Central Falls. This is the smallest municipality in Rhode Island by area. It's roughly 1.3 square miles, or approximately 3.4 square kilometers. Okay, so you can see this is where we have a cluster of simulated COVID locations, right? So Central Falls has a high proportion of racial and ethnic minority groups, as well as persons in poverty. Right? So the good news is that the Department of Health here in Rhode Island prioritized this community in the vaccine rollout efforts. A model here, it was interesting to see that validation that this was essentially where we had a high cluster of COVID cases. So the next steps for this work is to investigate other optimal or fixed adaptive bandwidths to create these cluster maps and quantify spatial uncertainty of COVID cases in a state like Rhode Island. Okay, so for example, for the fixed bandwidths, other methods such as the average nearest neighbor could be used as a potential bandwidth. This, could be based on geographic distance. In the adaptive part of things, this could be based on the number of cases. Specifically, this could be case adaptive, in which it could be sensitive to the abnormality of clusters formed by cases of communicable disease such as COVID. So fixed and adaptive bandwidths have different natures and serve different purposes. Basically, the values from the fixed bandwidth are more comparable in terms of spatial scale because they're all based on the same size of the neighborhood or the kernel. So basically, we'll not be comparing a value representing an area of a size of, let's say, 100 square kilometers with a value representing an area of like 10 square kilometers. Right. So in an environmental health project for a chronic disease, let's say cancer, the fixed bandwidth may be more suitable for detecting associations between hotspots with environmental factors. On the other hand, the values from the adaptive bandwidth are more statistically comparable, right? They have equal variances because they're based on the same underlying support, like the population or population density raster. So in this case, the adaptive bandwidth was a good one to consider for COVID mapping. The next steps for us would also, entail investigating the temporal dynamics of the classes. So we looked at one, scenario at this moment because it's work in progress. For understanding the cumulative COVID cases in, by December 9th, 2020. But we could do this, by month or by day and so forth. To see if these clusters, these model clusters have some spatial variation, or if they tend to move from one part of the study area or another. So yeah, the references that I alluded to, and just wanted to thank you for your time, and I just wanted to wish you good health, stay safe, and I'm happy to answer any questions that that you might have. Thank you.
Great. Thank you very much, Kevin. Yeah, folks, if you do have questions or comments on the research, if you could please ask them in the Q&A, that would be great. I did have a question looking at some of the simulated results of the mean p-value maps that you were showing there before you sort of dug into the smaller scale results. I'm seeing a lot of edge effects around counties. Can you talk a little bit about how those edge effects might have been created and what's going on in those?
Yeah, thank you, Levi. So yeah, we did notice that as well, and we suspect that this is an artifact of the bandwidth that we chose. We've not quite explicated the real reasons here for that, and this would be something that we keep in mind before actually generalizing this method for areas beyond Rhode Island. One suspicion that I have personally is something to do with the nature of the bandwidth itself. So since we did this by looking at, I'm just gonna go back to this slide, looking at the adaptive based on expected count. So this basically looked at the location of the cases in respect to the underlying population. And I think that, for those pixels that are close to the boundary, if they had high values, then they participated in this, modeling exercise in an irregular way. So what I think is if we are to change that to be adaptive based on the number of cases rather than the expected count, then some of these artifacts might disappear.
I see.
But with that in mind, because of the identified clusters in Central Falls, looking at the locations of the clusters themselves, we see that they're actually in the center of the municipality. And so this again came up as as a hotspot in quotes,
Sure.
and just to identify areas that might need further follow-up, rather than saying this is the only place in this whole state that deserves attention. So that's the caveat of such a method. As we're still tweaking it, we wanted to see that if some areas will still remain prominent, as we change the bandwidths and the kernels, right?
Yeah.
So with this method that we're exploring, Central Falls came across as a prominent, geography, right? That shows something interesting going on, regardless of the type of bandwidth and the size of the kernel, right?
Sure.
You might gain or lose a few pixels, but most of those would still be in that area. So that is what we saw, and we'll be keeping that in mind as we think about how to optimize this tool. That's a great question. Thank you, Levi.
Yeah, no problem. And then I also was kind of wondering, so when you run these two kind of competing Monte Carlo processes, one of them, the unrestricted one, ostensibly to establish a null, and then the restricted one to kind of develop this comparison method. Have you thought about sort of adding a bit more human information into that RCMC process to kind of reflect, I don't know, priors about where cases might be likely to occur in other kinds of diseases? Or have you thought about kind of adapting it to these sort of more micro-simulation driven contexts?
Yeah, great. So for COVID, we haven't done that yet. So here we've just looked at COVID cases and the outcome. In some of our previous work, we looked at cohort-specific measurements for modeling birth defects. So I'm a co-author on a 2013 paper that used this method to basically look at birth defects from children born of mothers between the ages of 15 and 49. So in that case, here in this, the RCMC part of things and the disaggregation of the locations of all cases are also based on cohort-specific information. So that's something we could actually do for COVID. Here the main assumption is that COVID was affecting people across the board. We could have done this, let's say, across the elderly, and, other subgroups, and that's something I think would have to do, right, in a more comprehensive way if we were to pursue this, to look at the nuances of COVID. But yes, to answer your question, yeah, there's an opportunity to put in certain population-specific parameters in the modeling. Yeah.
And then maybe I missed it, but when you're doing the population weighting for the resampling, which population raster were you using, or were you?
All right. So for this case, we used the WorldPop.
WorldPop. Okay.
WorldPop, yes.
Cool.
But essentially, any raster, right, with graded in a graded format could be used.
Sure. Yeah, and there are some good results out there that demonstrate, that WorldPop, let's say, compared to the high resolution settlement layer or what have you, has different behaviors in terms of their smoothing. So some of those population rasters will kind of over smooth and maybe give you more distributed weights than you might otherwise want. So interesting to choose WorldPop in that case, because WorldPop is known to be a little bit more concentrated than some of the other methods. So at least if I'm recalling that correctly.
Yeah, that sounds about right.
Yeah, that's very cool.
Thank you.
Does anybody in the audience have any further questions or concerns for our speaker? Going once. Going twice. Okay, well, no worries. Thank you very much for presenting today, Kevin, in our SAD seminar series. For those of you in attendance, I'd like to mention that our next seminar is next week, same time, same place, with Alistair Ray, formerly of the University of Sheffield, now at a startup of his own design called Automatic Knowledge Limited, who's going to be talking quite a bit about sort of visualization and analysis on communicating maps and statistics over an entire decade of his work as a cartographer and geographer, or I guess I should say data-driven cartographer. So please do make sure to sign up for that. And then also keep in mind that we have a series of interviews that are running currently. And our next interview will be with Helen Kuklelis on the 25th of May, supplanting a typical talk for the seminar series. So we hope to see you again very soon. And please thanks again to Kevin for the wonderful presentation today.
Thank you, Levi. And thanks everyone for being here. Have a wonderful day.
Bye all.